So hello, thank you for that introduction. Yeah, so I'm Tristan Childress, as he said. I joined the Bureau about a year ago. I'm not from Texas. I'm originally from Alabama, and I lived in Michigan for quite a while. But I'm getting to know Texas, and it's a beautiful state. It's enormous. I mean, it just goes on in all directions, and the different geologies and climates are fantastic. And so I'm rapidly learning about more and more about the potential of Texas. And today, I'm going to focus primarily on two projects that we're working on, which is doing field work out in West Texas and also doing some field work to collect lignite samples and their coal byproducts to determine their critical mineral potentials. And so, not to beat a dead horse, but, entering this critical mineral, I would call it almost a revolution of this energy transition. It's going to demand a lot more from our Earth, and we're going to have to do a lot more mining. And so just to give you a visual representation of what we mined in 2019, this giant cube represents the volume of iron ore mined for that year. And so for reference, this is the Burj Khalifa, standing at almost half a mile tall. And down here we have our Lady Liberty in New York. And so this is an enormous volume. And so primary drivers of increasing mining or increasing need for mining and critical minerals is the energy transition in the Department of Defense primarily. And so we have wind turbines coming on, solar panels, batteries, and just growing technology that all needs these things and is in competition with these various metals. And so I won't dwell on this, but the Paris Climate Agreement, in order to keep the global warming down below 2 degrees, 1.5 degrees by the year 2050, we're going to really need to increase mining of things like graphite, lithium, and cobalt. And so I think this presents a real opportunity for the mining industry to grow in the United States, as well as to build efficient and sustainable supply chains here in the US. And so to meet this 2-degree scenario, or to meet a net zero scenario by 2040 and 2050, will require quadrupling, if not sextupling, the amount of materials that we mine out of the earth every year. And so this figure, this visual figure, doesn't include things like cement or gravel or sand, which voluminously is much greater. So there's a huge opportunity here and a massive challenge that we as a country need to come together and figure out a way forward. And so we have been working with the USGS, who has launched the Earth Mineral Resources Initiative program, which is Earth MRI. And so they're working with 30-something states across the US. And we are working together to build large, publicly available and coherent data sets to promote data collection like topography, geology, geophysics, geochemistry, mineral deposit databases, and core hole availability. And so all of this data can go together to apply to exploration of mineral deposits, understanding our groundwater resources, having a better understanding of our energy availability, and better understanding our natural hazards. And so what the USGS has found is that for every dollar that the government spends on this type of work, industry will spend $5 to $6 as well. And so they were looking towards Canada and Australia and why is their mining industry so efficient? And that was some of their findings. And so now we're starting to do that as well. And so some of the products of this Earth MRI, which is occurring in several phases year over year, are these polygons that are mapped out across the United States where there are potential for various critical mineral deposit types. And so in Texas, we have about 20 of these polygons where you can find, hopefully they'll be useful to find various critical minerals. I need to clean this map up, but we'll probably make it publicly available on the Texas website soon, once it's kind of gone through the USGS process. But you can find this in previous iterations of these maps on the Earth MRI website. But here in Texas, there's lots of potential. We have the Texas coastal plain, where we have heavy minerals, we have uranium concentrations, we have these central Texas Llano area where there is known deposits of iron, graphite, rare earth elements, lithium bearing minerals, and other things like that. So I think this area can be used as a case for exploring outside of the Llano region. But there's a lot going on in Western Texas and as well as the Panhandle. And so West Texas is where I'm focusing most of my efforts right now. Hopefully I can bring a lot more people into the VEG to help me out and do this, and we can expand within the coming years. So in West Texas, it is home to this alkalic magmatism province. And so this province actually extends down into southern Mexico through Texas up into New Mexico, and even all the way up into Alaska, technically speaking. And so these magmas are strongly associated with rare earth element enrichment. They have a long history of mining in Western Texas, for example, the Van Horn Copper District and the El Paso 10 districts. And so we have newer proven resources of rare earth elements at Round Top in Sierra Blanca, Texas, marked out in this blue box here. And so if we have Round Top, are there other Round Tops in Western Texas? So to quickly kind of introduce you to Round Top and what it is a joint venture between the USA Rare Earth and Texas Mineral Resources Company. And they are planning to mine this rhyolite situated in Sierra Blanca. I really should have named this lignites, rhyolites, and cyanites, because most rocks out west aren't rhyolites. But anyway, so this mine has an estimated 20 years of mine life. It has an average annual revenue of almost $400 million. About a third of the income will come from rare earth elements. I'm sorry, a fourth will come from rare earth elements, and a fourth will come from industrial minerals. And then about a half of the income will come from tech metals from this mine. So what they're doing there is not just mining the mountain for its rare earth element content, but they are holistically mining it for its entirety. And really they're trying to pick it apart and put each element in a pile, and then they're going to sell that pile. And so that is kind of this idea of sustainable mining, is that you don't have waste, or you minimize the amount of waste that you create. And so in the foreground of the picture on the left is Round Top. It's about a mile wide and 1,200 feet high, I think. And so this isn't mountaintop removal. This is mountain removal. This will be gone in the future. It's kind of sad, but the reality is we need it. So Round Top is one of a series of about 5 rhyolitic intrusions in the Sierra Blanca area. It is a pretty typical lactolith that was introduced through a pre-existing dike that cross-cut the sedimentary layers and intruded in between the Del Rio clay and the Buda limestone. It is primarily made up of potassium feldspars, albite plagioclase, and quartz grains as well. And it has these really unique twinning, hourglass twinning in the K feldspar, which is thought to be a product of quick cooling in the area. The primary minerals that host the critical elements are yttrophlorite, yttrocerite, cerianite, chainbaite, I always can't pronounce that very well, and zircon. And so some key takeaways from these SEM images here is that these primary ore forming minerals are hosted in pores within the host rock. So you can see in this K feldspar where it's been dissolved a bit, there's a lot of porosity here, and you get lots of yttrofluorite and yttrocerite inclusions in the K feldspar. And then in this anite biotite crystal, you see that it has been dissolved away and then infilled by these later stage minerals. And so porosity here plays a big role in the economics of Round Top, which we need to think about in regards to the rest of West Texas. So what makes Round Top so economically viable is its enrichment in the heavy rare earth elements. And so in pink circles, the pink circles represent Round Top, and so you can see that their concentrations are 100 to 300 times chondritic concentrations. So that's pretty good. And Sierra Blanca is also enriched, but by a factor of about 3, Round Top is more enriched, and I think they're exploring the rest of the area as well. And so that led us to think about, where are the other Round Tops in West Texas? And the best place to start is where we know we have surface occurrences of these volcanic bodies. And so working with the USGS and with the New Mexico survey, we have this Cornutus mapping project where we were funded for activity for 2 years and slated to finish next year in around August. And so I spent last spring, mapping 2 quadrangles and collecting lots of samples, hundreds of samples for geochemistry. So, you know, the mapping is pretty much done. We've sent 86 samples out to the USGS for assay analyses. They're swamped, so we're still waiting on those, but I think they're going to be very, very interesting to help us build a bigger picture of what's going on in West Texas. And so, you know, we're going to review our work with some new data that's coming out and digitize our field maps and provide them in an easily digestible public format. So our exploration approach in West Texas is to take these base samples. So go out to all these outcrops. So we have the 16 Mountains quadrangle and the Sierra Diablo quadrangle. And immediately to the east of here is Del City, Texas. And immediately to the east of that are the Guadalupe Mountains. So while we're out there, what we do is take base samples. So we go to each outcrop, we find the most modally abundant type of rock that you can find and take a sample of that. And we're going to see what the geochemistry says of that. And then from there, you go on and look at all the weird stuff. So if you have weird discoloration, if you have contact rocks, calcite veins, anything that's strange that doesn't fit, you know, take a sample of that as well. And the geochemistry of that may tell you something very important about the rocks that you're dealing with, whether or not they exist or whether or not they have economic viability. And so what we found was that there are these quadrangle scale structures that actually can point you to underground concealed bodies. And this was later confirmed by aeromagnetic surveys. What I also found was that calcite veins tend to grow with frequency of size as you approach these bodies. And so the geochem and structural data and aeromag are all going to tell us a story that we can apply and we can use to inform the public to help direct more exploration efforts out in West Texas. So I probably have too many slides, so I'm going to cruise through these. But these are the Cornutus, and these lie right across the border of New Mexico. And so this is looking northward. Wind Mountain is in the background, San Antonio. This flat one here is Washburn, and then we have Chatfield Mountain to the right. And most of these are cyanitic intrusions, and some of them have nepheline in them, indicating that they're just really silicate poor. In the area, you get really strange occurrences of these iron-rich fluids and goethite, hematite mineralizations in the local Cretaceous rocks. We sampled these. We don't really know what's in them yet. I've looked at them in SDM. They don't really have much going on, but they are pretty fascinating. So, we definitely have these fluids that are coming off these magmas. We go down in the drainages and look for hidden outcrops and calcite veins. We found a few intrusions that were not previously mapped just by walking these arroyos and mapping them out. And you find lots of veins down there as well. So the arroyos are a good place to start if you're doing exploration out west. So we got these 86 samples. We cut them. These are just pretty typical images of them. So up here we have our nepheline syenite, and then we have some phonolithic dike rocks that they actually have really large limestone clasts in them. So they make me wonder, are they dikes or are they lava flows? I'm not sure. But then we also took samples of these veins to see if any magmatic fluids are in these calcite veins. And so within Miller Mountain, just looking under the SEM and doing EDS maps, we have found that there are rare earth element bearing apatites in there. There are these strange iron spheral droplet looking things that occur in sodic plagioclase, and within these iron droplets you get these calcic plagioclase, which indicate to me that this iron droplet and this calcic plagioclase came from much deeper within the crust. And so this represents a more mafic body that was differentiated and then eventually formed one of these cyanites on the surface. And so these are things that we're looking into to help build this story of how did these cyanites form in the first place. Some pretty interesting features, and I've almost convinced myself of this, which is bad form, but there are these iron-rich emulsions that are in the sodic plagioclase, and it looks like they have. So this is, I think this is our arfvedsonite, which is an iron silicate mineral, and I think this has been altered from perhaps magnetite or perhaps some iron melt that was originally there. But these seem to have formed around other crystals that formed prior to the crystallization of this iron phase. But you can see that they're titanium rich, which to me indicates that they are, well, they're certainly magmatic in nature, but polymorphic in nature. There are these aluminum-rich emulsions that come out of the sodic plagioclase as well. I don't fully understand what this is or why this is happening, but they tend to occur with these iron titanium phases as well. And again, we have these rare earth-bearing phosphates and some other minerals in there as well that seem to have rare earth elements. So really what we'd like to do is get them under electron microprobe and LA-ICP-MS to confirm these elements. So we did some surveying with the USGS, and there is a very complex network of volcanic intrusions in the area. I was pretty validated when we got this data, and what I was pointing to is concealed intrusions turned out to be true. I am a good field geologist after all. And so we'll kind of continue on through some of these. But we're going to continue this work in West Texas. We are applying for more funds for doing more quadrangle mapping in West Texas. There are a lot of outcrops and intrusions that are out there that need to be sampled for their elemental makeup, just so we can figure out, are they economic or not? And if we can get really good samples of them, we can build a picture and hopefully build a genetic model for what's going on in West Texas and hopefully identify more areas of economic activity or potential economic activity. And so for the Texas lignites, we are working with the Department of Energy on a project called Core CM, which stands for Carbon Ore, Rare Earth, and Critical Minerals Initiative for U.S. Basins. And so this is a really large project. We were awarded $1.5 million for, I think, 2 years. And so in phase one, we have our sampling campaign. So we're going to go through the entire Gulf Coast and sample lignites and any other type of coal that occurs, really. And we're going to sample their ash byproducts from the power plants. And we're going to analyze them for their elemental makeups to see if they have any critical mineral potential. And so we're working closely with processing plants, power plants, various universities, University of North Dakota, University of Kentucky, University of Wyoming, the USGS, the Alabama survey, the Missouri survey, and a handful of others. And so this is a really big project. We have a lot of stakeholders involved, and I think it's going to be very enlightening. And so this team, if you know any of these people, and you're interested in this, please get in contact with us. Bridget Scanlon is the head of this team. She's here at the PEG. Of course, I'm part of this, Bob Reedy, JP Nico, Richard Kyle, Christine Oilman. And from the USGS, we have Peter Warwick, Leslie Rupert, Jim Howard from the University of Kentucky, Charles Nye from the University of Wyoming, Nolan Thaker from the University of North Dakota, and Sheldon Landsberger from the University of Texas. And this is part of a NETL initiative. And so there's lots of this going on in the United States. And there are a lot of people involved with this. This is an older figure, so there are more people involved with this today. But our general idea here is that, as I said before, we'll go across the entire Gulf Coast and sample these coals as best we can. And so we want to sample the coal seams and anything strange that pops out from those coal seams. And we'd like to sample the ashes from the power plants as well, because a lot of our power plants aren't burning coal from the coast, they're burning coal from the Powder River Basin. And so even though the Powder River Basin isn't located in Texas, all the waste products are. So now that is considered a Texas resource. So once we get more data on this, we can start plotting this and we can start thinking about, what areas along the Gulf Coast may be productive for critical minerals. And are the lignites even potentially productive at all? We don't know, but we have some good data that says it could be. To think about this, we're thinking about the Cretaceous time and what it looked like, prior to the deposition of these coals. So we have our basins, we have uplifts where we can get sediment sources, we have volcanic intrusions that are spewing out ashes that potentially host the critical minerals that we're interested in. And so, where can all of this stuff gather that may be the most economic? And so when we start getting our data, we can compare this to this map of Cretaceous time and see if there's any correlation between the two. Presumably there will be. And so a lot of our outcrops occur in the Wilcox group and the Jackson group. And this is pretty typical looking coal. You know, we have our coal layers, we have our ash-rich layers, and then the shale lenses. And so we want to take a hard look at it all. And so where are the critical minerals occurring? What mineral phases are they occurring? Are they in the coal? Are they in a specific part of the coal? And so, you know, for this coal example on the left, you know, we have this ash-rich layer here and an ash-rich layer here. We want to sample those, and of course the coal that occurs next to it, because these are redox boundaries, so you can have fluids flowing through here and interacting with the coal and perhaps depositing more critical minerals. And so, for example, at Eagle Pass, this is a plot of the Eagle Pass coals, and they are enriched in the heavy rare earth elements, similar to Round Top. So this makes them, you know, potentially economically viable. And then if you look at their clays are actually not very enriched, except for one clay that is just off the charts enriched. And, you know, when I last looked at this data, we don't have enough information to say why that is, but it just kind of goes to show that it's important to sample everything if you can, because you never know when a clay is going to pop out and potentially be more economic than the coal itself. And so this is just a comparison between the two. We have the coals and the interbedded clays, and most of the clays are not going to be economic, but then we have C1U that is exceptional. And so, you know, are these clays enriching the coals or vice versa? Where is this enrichment coming from, and how is that happening? And so in summary, our rare earth and critical mineral supply, it needs to increase. It's going to increase. You know, how much will it increase is anybody's guess, but it's coming. And so this opens up a lot of opportunity for here in the U.S. to think about finding resources of conventional and non-conventional sources of critical minerals and rare earth elements. And I think we, as geoscientists, especially the independent geoscientists out there, need to get really creative on where they are looking for these rare earths and critical minerals. West Texas, I think, is just a really fascinating place. There's a lot of stuff buried out there that no one has really taken a hard look at. There hasn't been a lot of deep drilling going on, but there is a long history of mining and metals formation out there. So I'm very curious to learn more about it and to build a coherent genetic model for West Texas and to figure out if there are more round tops out there. Cornudas, Texas, we're waiting for assays. It's a really interesting place. Gulf Coast Lignites, that's a new project, but it's kicking into gear right now. I think we'll have a lot more to say in a few months. But we're doing a lot more work too in the United States, in Texas. So we're doing critical minerals related work involving Smackover shales, produced waters from the Smackover, various waste streams from graphite to bauxite, potentially other things. And so, you know, that kind of goes back to being creative about thinking where can you find potential source of economic stuff to put back into the economy. So if you're curious to know more, I encourage you to email me or give me a call sometime. But we have our website, beg.utexas.edu/minerals. We have a mineral resources map that you can go, and this kind of shows a layout of previously mined minerals and where their occurrences are, and the sources for that information. So it would be very useful for anyone who's interested in learning more about critical minerals in Texas. The website needs updating. That's something that I need to do soon, and I will get on that. But with that, I'll say my piece. So thank you.
Thank you so much, Tristan. That was a great talk. There are lots of accolades in the chat for your talk just now. Everyone really enjoyed that. Thank you. There are a few questions for you. We've got about 3 or 4 minutes. Are you able to see the chat, or maybe if you stop sharing your screen, Tristan, you might be able to see some of the questions, or I can read them out for you.
I can see them.
So back up to about 10:55, Ravi Nandigam asked a question about Big Bend National Park. Do you see that one?
Yeah, so are the round top mountain type heavy rare earth rich zones expected to be present in the Big Bend National Park area? And Ravi, I don't know the real answer to that question, But yeah, I do think so. Big Bend has been a very active area, and so if you can see the slides, you know, you can see the slides. These pink dots down here, a lot of them are fluorite type minerals, and so fluorine is a huge ligand for transporting rare earth elements, and so I think it is down there. And USGS and us have talked about this, and one reason that we're not trying to focus in that area so much is because it is national land, and so development of that land is not going to happen. I do think we need to go down there and study the rocks just so that we can add it to the West Texas model, because it's very important. You know, it's a huge piece of the puzzle. But yeah, I do think it's down there, and if you can go down there and find it outside of the park boundaries, you could be rich. I'm very optimistic. I used to be an exploration geologist, so you know, I'm just I'm not cautiously optimistic, which is probably a bad thing. But so, and then is the calcite in those veins carbonatitic? Any odd geochemistry suggesting a mantle source? So that's what we're looking at, Adrian, is that the calcite is curious because it only occurs around the intrusions. And initially I thought it was perhaps remobilized material from the limestones, but we don't know yet. And we're going to do fluid inclusion work, and I'm going to do some isotope work as well. And I think Alex agrees with that. Jesse says, I don't think Round Top has been proven to be economically viable. Round Top Mountain is only a PE level project, so economic feasibility is unknown. Yeah, that's true. Round Top has a history of saying they're only a few years away from production. So I am curious to see where they go. Rare Earth USA, as I'm sure you're aware, Jesse, their whole thing is to keep their rare earths on the US continent, on the North American continent. And so they want to mine it, they want to separate it, refine it, and put it in magnets and sell those magnets to Americans. So, you know, it's an interesting take, and I wish them well. And then yeah. And so, are you going to investigate any of these shale plays since they contain lots of ashes? Yeah, we're actually talking about that now. Julie Bloxham from oh my gosh, I forgot the university. Julie Bloxham, she's in this talk. She's we're working with her from Stephen F. Austin University, and Ashley Downs. And so we're thinking about putting a project together with to do exactly that. So yeah, and that looks like the last of the question. So I'll leave it at that.